And so much of my early work was trying to make sure that I could actually make these methods competitive on modern GPU-type hardwares. And I think we've succeeded in a large part, especially if you're using explicit time stepping, which for waves I imagine you are. So I'm going to talk in this talk a little bit about stability and how to design DG methods which are both stable and efficient in the context of complex heterogeneous media, starting with a much more simple wave equation. So this is a brief idea of why DG methods work well. If I just take a general mesh, just imagine that it's captured some geometry and is given to me, then it's made up of individual little elements. So I'll operate on this simple one-way advection equation just to illustrate what DG does. And if I take individual elements, then DG essentially operates just in 3 steps. It decouples it so that I can evolve the solution on every single element basically independently. I start by taking an element and computing a flux, basically transferring a little bit of information between one element and its neighbor. This is the only non-local step. I then have to compute basically the right-hand side of an ordinary differential equation, which basically looks like the actual differential equation. You have an x derivative and then some flux term, which enforces kind of a weak continuity between different elements. And then once I have that right-hand side, then I just evolve it in time. And that is DG method in 3 very basic linear algebraic steps. You can use whatever you want, Runge-Kutta, Adams-Bashforth, whatever you'd like. It generally works with any time discretization. So you have essentially 3 steps: an update kernel, which updates a solution in time, a volume kernel, which applies essentially a volume differentiation matrix, and then a surface kernel, which basically takes this numerical flux and propagates it into the internals of the element in some way. We'll go into how to make these each efficient later on. And what got me interested in DG methods for seismic applications was when I was in my postdoc a long time ago now, and we tried to look at wave propagation in heterogeneous media. So I thought this would be easy. The wave equation is solved, right? Everyone has done it. But I was looking at a very simple case. For finite difference folks, this is no big deal. Take a smoothly varying medium and try and propagate a wave through it. So what I found is that discontinuous Galerkin methods typically have this limitation that if you have a smoothly varying heterogeneous medium, most people will typically approximate it using piecewise constants. So over every little triangle, you'll just take the wave speed, average it, and use that as the true wave speed in your model. And if you do that, then you can kind of see in this first picture, in this middle picture, you get some weird oscillations which show up. You're trying to approximate something that's smooth with something that's discontinuous, and so you have these weird spurious reflections which appear, and this is something that's generally problematic for simulations. So digging into the mathematical finite element literature, it's not too hard to find that, well, if you instead approximate the wave speed on each element using a high order polynomial, something that varies smoothly, then you get this nice, beautiful solution which accounts for the differences in wave speeds and is energy stable, but unfortunately is really inefficient to compute with. And this basically boils down to the fact that if I'm solving a system of ODEs, then a traditional finite element method requires you to invert a mass matrix at every single time step. For just a homogeneous medium, this is no big deal. For piecewise constant heterogeneous mediums, this is really no big deal. But if you have smoothly varying media, then you have to actually compute this mass matrix, and then invert it, store the inverse. And because the wave speed varies over every single element, you have to do this for every single element over and over and over. And this is what made things kind of expensive. So these are the 2 stable methods. I'm ignoring the unstable methods because I just didn't want to deal with them. But I was left with basically something that's cheap and inaccurate, something that's expensive and accurate, and then stuff that just didn't work in my opinion. So what we did was we went through and it started to explore different types of methods, and we found that it was easy to actually restore accuracy and efficiency with this adjusted method. We called it a weight-adjusted DG method, and I'll illustrate how you construct it for acoustic wave equations. We then started exploring and found that it gave us a lot of benefits for also elastic media, coupled elastic media. We found out we could make it really fast using some Bernstein Bezier tricks, which some of you might have heard in Andreas Atlay's talk recently. And then we've recently started to work in poro-elastic media, and I'll conclude the talk by showing some of the results there. But let me try and explain simply what actually this is. So the entire issue that I have with these traditional higher order DG methods is that I have to store and invert a mass matrix, and I have to do it over every single element of my mesh. So what I do is I actually take this weighted mass matrix, this term on the very far left, and just replace it with what I call a weight-adjusted approximation. And you can see it kind of makes sense. I have if c squared is going to be the wave speed, then I have a mass matrix weighted with the inverse wave speed. And so if you invert that mass matrix and then invert the wave speed, that kind of looks consistent. It turns out this is consistent, high-order accurate. It turns out it's actually energy stable as well, so it checks off most of the boxes that we want. And there's a lot more theory that I can show to kind of back this up. But one thing that was really nice for us is that it also was really easy to implement. This was a small trick, but it basically let us break our implementation up into the implementation of a DG method for a constant wave speed, homogeneous medium, very easy to work with, and then a modified update kernel. And I'll talk about how to make this modified update kernel really fast later. What was also nice for us computationally was that this was a low storage method. We never actually have to form these matrices, whereas in the previous case we had to store, we had to compute, invert, and store all these matrices, and this memory was really costing us. So I'll just, come on, there we go. I'll just hit some quick highlights of why I think this is interesting. Mathematically, I was interested to make sure this didn't do anything bad to our DG method. If we're using explicit time stepping, turns out that it generates essentially the same constants of norm equivalence as a standard high-order DG method. So it doesn't affect the CFL. I can march at the same time step that I did before. If you're interested in local conservation or high-order accuracy, we have some theorems that show you can do that. But what was really interesting to me was when I discovered that the difference between my traditional DG method that's expensive and this new method was essentially order h to the n plus 2. This is important to me because the best I can do in approximating a function using polynomials is order h to the n plus 1. So my accuracy of my simulation is going to be order h to the n plus 1, and the difference between the new and the old method is actually going to be smaller than that. What this means in practice is, if I can get the slide to change, here's an example of a smoothly varying wave speed, a little discontinuity in between. Here's a standard DG method, and if this will change, here's a weight adjusted DG method. I can switch back and forth, and visually there's just no difference whatsoever. I think I can switch back and forth. Maybe not. I'm going to assume this is a one-way pointer. All right. And when we tested it on GPUs, it turned out that it was actually faster for some reasons which I'll explain in a second. But if I look at the speed up of actually just inverting this mass matrix or pre-computing and storing the inverse of this mass matrix, this new weight-adjusted DG method gets a speed up about 2 times, a little over 2 times for 4th and 5th order approximations. It goes down again, we'll deal with that later. But essentially, this fact that I've transformed this into a low storage implementation made things much nicer for graphic processing units. So this works because, well, if you want efficiency on GPUs, you don't focus on the flops. Flops are essentially free. You focus on the memory accesses and the bandwidth that you have. And if I want to store and if I want to pre-compute and store inverses to all these local blocks, then I have to basically shove all of these matrix blocks through a GPU, and that eats up all my bandwidth. And if I look at a modified weight-adjusted DG method, I have a few more computations, but essentially what ends up happening is I have multiplication by a block matrix, multiplication by a block matrix, except all those blocks are the same. So I just have to store 2 blocks for every single element in the mesh, and then just stream through a bunch of scalar vector data, and this works much better on his GPU than this other approach. Okay, so that's what we found quite a few years ago. And then we started to explore, see what this could actually buy us in terms of improved performance for different methods. So we started looking at elastic and then coupled acoustic-elastic media. I don't know what is going on there, so I'm just going to click. OK. And we found out that being able to deal with these weighted mass matrices in a smart way actually let us use much more exotic, let's say, stranger formulations, which simplified our lives. So what I did was I'm taking this formulation, which actually appeared in 1978 from one of Tom Hughes's papers. It's a symmetric velocity stress formulation. And the important part is that I'm taking this constitutives tensors, this C, and basically multiplying it over onto the time derivative. This is basically the same as taking the wave speed and moving it over to the time derivative. It's a small thing, but it ends up really simplifying down the construction of discontinuous Galerkin methods for this problem. What it does is it basically takes all of the media heterogeneities and moves them away from the derivatives and the discretization. So all that's left on the right-hand side are these incredibly simple matrices. All these A sub I matrices, just ones and zeros, really straightforward. And then we end up, when we discretize in a DG method, we end up with this now matrix-weighted mass matrix. So it's a fully coupled, large block system. It's even more messy to work with, and it turns out that we can apply this weight-adjusted approximation again to basically invert this or approximate its inverse in a really cheap, high-order accurate, and energy-stable method. So, all right, I think I'll just use a mouse. The reason we liked this at first was because it was really easy for us to incorporate basically different types of media. By separating out all the media heterogeneities from all the rest of the physics, we're able to switch between isotropic, anisotropic, all the types of elastic media in the middle without really changing our implementation at all. So here's a reference solution from 2000 where the authors of SpecFem compute coupled elastic, isotropic, anisotropic wave propagation. And we are able to reproduce that fairly well using this modified weight-adjusted DG method. And in my opinion, it was much simpler for me to compute this figure on the right than it was to do one on the left. We also started working with elastic and acoustic coupled media, and we found that being able to factor out the wave speed away from all the rest of the physics also simplified the coupling terms. So I'm going to consider it a simple coupled elastic acoustic medium where I have some stress variable sigma, some velocity variables v, pressure variable for the acoustic medium, and then velocity variable for the acoustic medium u. And then in this little box over here, I have all the coupling conditions. So across this interface between the elastic and acoustic medium, I enforce that the normal component of the stress is equal to the pressure times the normal vector. And then I have that the velocity has to be normal continuous across this interface. And what makes elastic acoustic coupling complicated is that for discontinuous Galerkin method, these coupling conditions typically lead to really complex numerical fluxes. So these fluxes that I use to compute continuity between different elements and between different types of media, they look like this for, let's say these are traditional upwind fluxes. If you're familiar with the DG literature, these are sort of the gold standard fluxes that you always want to try to use. And this is for isotropic media. For anisotropic media, there's actually no explicit formula, and it gets even more messy. But deriving these fluxes is a fairly opaque process. And moreover, if I try and use these fluxes, it turns out I can't even show that things are energy stable in the case of smoothly varying heterogeneous media. So for us, what we found was by factoring out the heterogeneous media, the media heterogeneities, away from the rest of the physics, we end up with very, very simple fluxes where essentially the consistency and the continuity conditions show up directly in our fluxes. So these are just pairs of fluxes for stress and velocity for the elastic media and for the acoustic media. On the top, you basically have terms in blue that are for consistency, basically to ensure accuracy, and then you have some terms in red, which are optional. We've added these to essentially damp out spurious components of the solution. And in both cases, they basically just look like the continuity conditions between two interfaces in an elastic medium and an acoustic medium. And if we look further and go to the case when we have coupled elastic acoustic media, then the interface coupling remains relatively simple. So we need continuity of the normal component of the pressure, the normal component of stress and pressure, and those show up directly in our fluxes. I wish I had a slightly longer arm, but this term down here, that's exactly the same continuity condition that we have directly from the physics. The continuity of the velocity shows up directly in these fluxes as well, and they show up the same way in all these penalty terms. Basically, these fluxes are really simple and straightforward to construct a priori. We did have one slightly strange term, which is just written in black in the top middle, and that I just need to add in. Kai Hong found that we need to add that in just for stability purposes. But apart from that, I thought that the construction of these fluxes were relatively intuitive. So if we use these fluxes, if we start to simulate things, if we look at simple solutions for Snell's law and for Schulte waves, then we get higher order accuracy, just as we expected, with a relatively simple formulation. And just to make sure that things looked right, we took the same example we had of anisotropic and isotropic elastic medium, and we modified it to include a little corner with acoustic media as well. So we start off with a Richter pulse directly in the middle, and when we evolve it in time, we basically see that the results look kind of like they did in the case when we had isotropic and anisotropic coupled elastic media, except in the top right-hand corner, it basically looks like an acoustic wave. So you can see the same behavior, except now you see this nice little Schulte wave propagating along the elastic-acoustic interface, and things otherwise look the same as they did in the anisotropic, isotropic case. And if we wanted to incorporate smoothly varying wave speed, well, that pops in, still remains energy stable, still remains high order accurate, and things generally work. Okay, so we were exploring basically the space of how to apply these DG methods to different problems in wave propagation, but of course nobody's really interested in these if they're slow, right? So this is the problem with finite element methods, I think, is that they have a reputation of being much more expensive than finite difference methods. And while I don't think they're going to be entirely comparable, what we've done is we've tried to close the gap a little bit. So this is one thing that we also faced a while back. If we increase the degree of the polynomial, we generally want higher and higher order to get lower and lower dispersion errors and dissipation errors. Well, it turns out that the cost basically skyrockets. We have those 3 steps to a DG method, the update, surface, and volume kernel, and each of those basically blows up in cost as you increase the degree of the polynomial. And this is because, well, we're doing just matrix vector multiplications, but they're dense matrix vector multiplications. And the size of these matrices grows fairly quickly with the degree of the polynomial. So what we tried to do is we tried to reformulate this method to reduce the cost, and this basically amounted to a change of basis. It turned out it was as simple as that. Typical discontinuous Galerkin methods usually use a polynomial basis represented using a Lagrange formulation. So you have a set of nodal points, they're good interpolation points, and you can define a polynomial basis based on these points. This simplifies the computation of fluxes, it simplifies a little bit some of the derivation of matrices, but it turns out that it creates dense matrices which are really expensive to multiply. Turns out if we switch to a Bernstein basis, something that's been long used in computer graphics and computer-aided geometry, then all the differentiation matrices that pop out become incredibly sparse. Turns out you can actually show that there are at most 4 non-zeros per row, so you basically get something that looks like a sparse version of a very compact bandwidth matrix. And applying this suddenly becomes really cheap. So this is a differentiation matrix. The second part, the lift matrix, is a little more complicated, but it turns out that we can also apply this in a really, really quick way. So we have this sort of slice-by-slice approach where we march through different slices of a tetrahedron or a simplex, and it turns out this also achieves the same asymptotic level of complexity. Basically, let me just summarize in this slide. If you take the volume and surface kernels and replace your nodal bases with Bernstein bases, then you get a runtime which looks like the one on the left, dropping down to a runtime which looks like the one on the right. It looks much more feasible. We see basically increasing factors of speed up. At n equals 9, we see about a 4 times factor of speed up. Wait, no, I think it's larger than 4 compared with traditional DG methods. The last step that we had to deal with was the fact that, well, we accelerated 2 kernels, but there's always going to be a bottleneck. And the update kernel was a lot more difficult for us to deal with. And it turns out that we had to do a little bit more work to get things fast. So what we did was we started working with the wave speed. Instead of looking at the exact wave speed, we said, what if we approximate it using a polynomial? Using a constant polynomial, then you get a piecewise constant approximation, which, as we saw before, isn't great. But we can increase this to a piecewise linear polynomial. We can increase it to a piecewise quadratic polynomial. And in doing so, we can get increasingly more resolution and basically tune this to the amount of accuracy that you need. And then we can exploit the fact that weight-adjusted DG method basically performs at the mathematical continuous level 2 steps, a multiplication of 2 functions, and then an L2 projection. And if we assume that both our solution and the wave speed are polynomial, then we can make both of those steps really fast because there exist really fast Bernstein algorithms for polynomial multiplication and polynomial projection. So this is, again, work that Kai Hong did, and we were checking to make sure what the accuracy was. You can see here that as you change the degree of approximation of your wave speed, you get different levels of accuracy. But what got us really interested was the fact that polynomial multiplication and projection were fairly fast in a Bernstein basis. So let's say I have a piecewise linear representation of the wave speed on the left, this element with four C's, C1, C2, C3, C4. And on the right, I have some high order representation of the solution on a tetrahedral element. If I want to multiply these two together and produce a higher degree polynomial, then this amounts to the following algebraic operation. I take these 4 matrices, multiply them by the solution, and then scale each of them by the constant on each of the constants that make up the wave speed on the left, and that's it. So if you just look algebraically at what's going on, this is a fairly fast operation. And again, it's asymptotically fast, order n cubed. You can't go any faster than this for this type of method. If I want to do fast Bernstein polynomial projection, that ends up being a little trickier, but it's also not impossible. What we do is, with the following step, we take the wave speed multiplied by our velocity or by our pressure, and that becomes a higher degree polynomial. If we want to project it down, then we have to represent this polynomial projection matrix as basically this formula involving, these are called degree elevation matrices, which take polynomials of a certain degree and then move them up or move them down. Long story short, these are really sparse in the same way that those differentiation matrices are sparse. And if we rewrite them in a certain way, then we can rewrite them in this telescoping form and get something that's order n to the fourth complexity. It's not optimal, but it's pretty close to optimal. And a little sketch of our algorithm for the GPU, we basically have something that doesn't look like it would do super well in a streaming architecture, but it balances the use of register memory, shared memory. It tries to minimize the number of memory accesses at every single step. And if you actually look at the scaling of the runtime, it delivers what we expected. So just a reminder, the traditional method of the traditional weight-adjusted DG method, the cost scales as order n to the 6 in 3 dimensions, and that's the blue line over here. And the solid blue line basically is the recorded runtimes on a GPU. And you can see that, well, it's pretty competitive for n equals 2, 3, and 4, but as you increase n higher and higher, the cost basically balloons and skyrockets up. Whereas if you use Bernstein-Bezier DG with either m equals 1 or m equals 2, piecewise linear or piecewise quadratic approximation of wave speed, then things basically scale pretty well. They achieve this asymptotic complexity of order n to the fourth, which is what we predicted. And they handily beat traditional weight-adjusted DG methods at very high orders of approximation. OK, so I think I have about 5 minutes left. And with this, I'd like to tell you a little bit about what we've been doing more recently. We've been looking at extending this to poro-elastic media. And this work started because Dr. Martin de Hoop was interested in looking at a poro-elastic system. And I thought, well, maybe this weight-adjusted DG method works well for it. This was maybe one of the most straightforward extensions of a method I have ever seen. And I'm very grateful to Dr. de Hoop and Kamraj Shukla for helping me put this together. So a poro-elastic system is basically an elastic system with just a few more variables. What you'd have are 7 stress components. So you have the 6 stress components in an elastic system, a scalar fluid pressure, which is separate, and then instead of having 3 velocity components, now you have 6 of them. The reason for that is because in the derivation of this poro-elastic system, you assume that you have different fluid velocities in both solid and fluid media. So you're assuming sort of a pore scale mixture of solid and fluid media. Basically what this does, this expanded system produces, it supports 3 different types of wave speeds. So in an elastic system, you get a pressure wave, which travels the fastest in this picture on the left. You get a shear wave, which is the second ring, travels slightly slower. But then a poro-elastic system actually supports a third wave, a slow P wave, which you can see is that small circle in the middle. And while this looks fairly normal for orthotropic sandstone, it turns out for complex materials like epoxy glass, then you get some really weird kind of refractory behavior. And it turns out that if you write this as a system of equations, then the structure looks almost identical to that of just linear elasticity. So applying weight-adjusted DG to this was a straightforward extension. And what we found is that we get the same benefits. If we take a, let's say, relatively fine mesh and a relatively low degree polynomial, then there's really not a big difference between using standard DG methods and weight-adjusted DG. But if we start increasing the polynomial degree and decreasing the mesh resolution, what's on the left is the traditional DG method, and you start seeing these oscillations show up. And as I increase the degree of the polynomial higher and higher and reduce the number of elements down even further, then you can see that the left picture, the left simulation basically looks completely corrupted by noise, and the right picture simulation looks exactly like it did before. So we get higher accuracy, we remain provably stable, things essentially work, at least for this litmus test. But what got us interested was, well, we wanted to see how well this compares with other existing approaches too. So we compared against SpecFEM, and this is a poro-elastic heterogeneous medium with a top layer and a bottom layer. And if we just let off a Ricker pulse and let it go, we can see very clearly that we have I have labeled here 1, 2, and 3, and 4. These are the 3 different waves that you expect in this system. and our approximation of them matches up pretty well to SpecFEM. If we go on, we can take a look at a more realistic simulation. Here is a model reservoir problem geometry that Raj set up. And we have a couple media heterogeneities inside there, fault lines and so on. And if we look at something like the horizontal fluid particle velocity, you can see waves that propagate, and the horizontal solid particle velocity propagates slightly faster. It remains stable. We expect it remains higher order accurate. We obviously don't have an exact solution in this case, but things look essentially like they should, and we're working on validating these methods right now. Okay, so let me try and conclude. If you've listened to this talk and you're not at all interested in discontinuous Galerkin methods, that's fine. Turns out all this theory can actually be extended to finite differences using a specific approach called summation by parts finite difference operators, which basically try to mimic the structure of discontinuous Galerkin methods at the matrix level. We're also currently working on extending this to moving meshes, where this will end up giving you sort of local adaptivity without the complex topological changes that local adaptivity usually incurs. And we're taking all these lessons, and most of my recent work in the past 3 years has actually been on extending approaches similar to this to nonlinear conservation laws with shocks and rarefaction waves and much more dense complex physics. But with that, we think we have something that works generally well for linear heterogeneous medium for wave propagation in all these types of systems. And we're looking forward to seeing how far we can go with this. I'd like to thank Total AMP, who supported this in the beginning back in 2015 and 16, and it has more recently been supported by the National Science Foundation. So thank you all for being here, and I welcome any questions you might have.